Greetings to everyone, I'm Manuel De Stefano and I'm presenting the work that Fabiano Pecorelli, Damian and Tamburri, Fabio Palomba and Andrea De Lucia and I have made that is called Splicing Community Patterns and Smells, a preliminary study. I'm Manuel De Stefano, I'm a master's student in computer science at the University of Salerno, and those are my contacts if you want to keep in touch with me. So let's explore the agenda for our presentation. First of all, we have a brief introduction of what community smells and community patterns are. Then we have the definition of the study design that we have conducted, followed by the discussion of results and validity of our study, and then a brief conclusion with the proposition for our future works. So let's begin. What are community patterns and community smells? Of course, we know that software development is a social activity. Indeed, software is developed in team. But nowadays, software is increasingly being developed by globally distributed communities having complex social networks. And these social networks have been object of several studies. Some of them pointed out the alignment between social and technical community with their effect on the quality of the software produced. On one hand, some technical common governance mechanism adopted by open source practitioners to manage the community have been elicited, that are called community patterns. And on the other hand, some community-related factors that can increase the criticality of source code quality issues have been studied that are called community smells. So what actually are community patterns and smells? Community patterns have been elicited in a work made by Tamburri et al. In 2018. Community patterns, as said, are common governance practice that are made up by software development communities. As an example, we have formal groups that are groups made up by people which are explicitly grouped by corporation to act them. To be more precise, these people are grouped together as they have a common organizational goal called mission. On the other face of the medal, on the darker face of the medal, we have community smells that were investigated in a work by Tamburri et al. In 2013. Community smells, recalling the more famous term of code smell, are suboptimal and bad community decision, community structures that could affect an open source community. For example, we have the bottleneck, in which one member interposes herself into every formal interaction across two or more subcommunities, with little or no flexibility to introduce other parallel channels. The effect that this produces is quickly understandable, as one person interposing herself in any type of communication means a great overhead of communication. So, here comes our study, what we have done. Our study was moved by a single research question, that is, what is the relation between community patterns and smells? To be more formal, our goal is to investigate the relation between community patterns and smells, with the purpose of understanding whether the structural organization of a community may potentially lead to some sort of social debt, in the perspective of both researchers and practitioners. The context of our study is made up by 3 elements. The first and most important one, maybe, is made by the projects, or rather, by 25 open source software communities that comes from GitHub repository. The second element of our context are the community patterns. 9 community patterns that are detected by a tool, Yoshi, that we will see briefly. And the third element are the community smells. 4 community smells that are detected by another tool called Codeface for Smells that we will see shortly. What regards community pattern detection, we have Yoshi, a tool presented by Tamburri et al. In 2018. Yoshi is a social network analysis tool that is specifically designed for detecting open source community types. To be more specific, the community types detected by Yoshi are the 9 presented here in this slide. To cite some of them, we have a community of practice, informal networks, work groups, project teams, or informal communities, and so on. Yoshi is able to detect them with a 2-step approach. On the first step, given a GitHub repository, it mines commit history, issue tracker, contributors data in order to compute some metrics that characterize the structure of the community. Then, these metrics are given in input to a decision tree that is able to classify the community in one of the 9 types proposed. On the other hand, we have the community smell detection, made possible by Codeface for Smell. Codeface for Smell is a tool presented by Tamburri et al. In 2019, and it is a fork of Codeface, a tool that was originally designed to extract coordination and communication graphs, mapping the developers' relations with a community, within a community. But Codeface for Smell augments these graphs with the detection rules able to identify the 4 community smells listed here. As an example, the identification of lone wolf is based on the detection of development collaborations between 2 community members that have intermittent communication counterparts or feature communication by means of an external intruder, not involved in the collaboration. So, to what regards the data collection and analysis, a 3-step approach was implemented. In the first step, we have the detection of community patterns, exploiting Yoshi. In the second step, we have the detection of community smells that was possible exploiting Codeface for Smell. And then in the third step, we have association rule discovery, when the a priori algorithm was employed to mine the association rules between patterns and smells, and then these association rules were evaluated through 2 important metrics that are support and confidence. For each association rule in the form of R left and implies R right, we have that the support is given by the ratio between the co-occurrences of R left and R right over the total number of co-occurrences, and then we have the confidence that is made by the ratio between R left and R right co-occurrences over R left occurrences. These 2 metrics are a sign of significance of the rules detected. So, what has come out? Analyzing the association rule discovered using a priori algorithm, the first noticeable outcome is that when not filtering association rules by support and confidence, relationships between smells and the communities were found, with all the communities were found, except for formal networks. But considering only the most significant ones that are listed in the table presented here, we have that some relationships were expected, such as the one between formal groups and bottleneck, or between informal community organizational silo effect, or informal community and lone wolf, and so on. But some of them were unexpected. For example, the relationship between networks of practice and bottleneck. And these unexpected relationships were object of further investigations. So, taking an example of an expected relationship as mentioned, we have that the formal group implies a bottleneck. This is quite expected, as formal groups are formed by people which are explicitly grouped to reach a single specific mission. The problem arises when, in the case of two groups need to communicate. In this case, it is usual that such groups communicate by means of a representative, a liaison if we want to call it so. And this naturally leads to the introduction of a bottleneck instance, because all the communication between the two groups happen through these representatives, and so the overhead is very huge. An example of unexpected relationship is made up by a network of practice that implies bottleneck. Network of practice should be quite efficient in theory regarding communication, because network of practice puts together communities of practice that have proven to be groups in which interactions are frequent and collaborative. But sometimes happens that some members of these network of communities of practice interpone herself, act as a middleman between the two groups, and thus creating a bottleneck relation, a bottleneck instance. So the most important finding with our experiment is that different community patterns relate to different community smells. And the reason behind this is the presence of smell are related to the characteristics and peculiarities of the community patterns. Indeed, there are some threats to the validity of our study. First of all, to what regards construct validity, we have that both Yoshi and Codeface for smell are validated tools, and so no bias was introduced during measurement. And to what regards the mapping between theory and practice, we have that the operationalization of communication and collaboration comes only from GitHub, so no bias introduced. To what regards conclusion validity, we have the usage of a priori algorithm that could cause some problems. However, a priori algorithm is widely adopted and validated, so there is no problem in using it. And thus, only strongest rules were discussed, and so only the most statistically significant one. Finally, the external validity of our study is affected by the fact that only 25 projects were considered, and also for the reduced number of patterns and smells were investigated. And thus, this directly leads to our future works and to our conclusion, because we have already planned to replicate our experiment on a larger project dataset. And also, we have already planned to make further analysis on community patterns properties and the possible impact that organizational decision could have on social debt. And finally, in the end, more awareness wants to be reached about this. So we have planned to conduct a survey on the investigated communities to furthermore investigate the found associations. Thanks for your attention.